Alright, so we're going to compare all of these methods that we've seen of apportionment, and we're going to kind of take one example and we're going to do all the methods with the same example. So we're going to use 180 representatives, and we're going to use these 6 districts, District A through F, and we want to allot representatives using all the various methods. So what I want you to do is I want you, just given this data, push pause on the video and find out how many representatives using Hamilton's method. Okay, so hopefully you've done that. And let me, I'm going to do it really quickly. Basically, the population here is 12, 9, 32. That means the standard divisor, if we want to have 180 representatives, is about 71.84, and the 4's repeat. So that is the divisor in Hamilton's method is the standard divisor, 71.84. Now, I divided by 84, or just means 71.84. So we get a modified quota of, in every case, 63.721, 7 point, and why I say modified quota, this is the actual quota in Hamilton's method, 27.574, 4.593, 44.736, and 31.554. All right. Now, if we take the lower quota, 63, 7, 27, 4, 44, 71, add all those things up, you get to 176. So I need to put in 4 more representatives, and the places that I'm going to put those are going to be in the highest decimal. So if you look through the highest decimal, the 8 here, 736 is the next highest. Next highest is 721. We have a 5.7, a 5.9, and a 5.5. So the 5.9 is the best one. All right. So the number of representatives is 64 for District A, 8 for District B, 27 for District C, 5 for District D, 45 for District E, and 31 for District F. Okay? And by the way, if you add those things up, you will get up to 180. So we do have the right amount. 64 plus 8 plus 27 plus 5 plus 45 plus 31. All right. So that's how to do Hamilton's method. Now, we're going to, at the end, look at comparing all the different methods. But for right now, we'll just leave it at where it is. So let's take the exact same method, or excuse me, the exact same data set, and I want you to use Jefferson's method. Find the divisor, and then find the quotas and the number of representatives using Jefferson's method. Push pause on the video, do that, and come back and see if you got the right answer. Alright, so hopefully you did that. Now, I wrote the standard divisor here as 71.84. You see that pop up. So our divisor, remember, is going to be less than that in Jefferson's method. And after about 3 iterations, I got a divisor of 70.5 that would work. Now, the modified quotas here, again, we're just dividing by 7.5. Is 64.8. 0.93. Oh, excuse me. Let me rewrite that. That looks awful. Sometimes this pen doesn't write very well. So 64.94, 7.97, 28.099 or 28.1, 4.68. Again, in Jefferson's method, I don't have to worry about how I round these. In Hamilton's method, we had to worry about, going out a few decimal places so we can compare. But in this method, you don't care about how many decimal places you go out because you're always going to use the lower quota. So we have a modified quota here. Number of representatives will be 64, 7, 28, 4, 45, and 32. Okay? And if you add all those up, 64 plus 7 plus 28 plus 4 plus 45 plus 32, you do get up to 180 representatives. So again, I want you to do the same thing with Adams' method. I'll write the standard divisor here before I push pause. So you push pause, do this allotment using Adams' method, come back and see if you actually got it right. Alright, so when I did this, the divisor that I got that I wanted was 73.1, and it did take me a while to get that. But once I've got 73.1, the modified quotas here are 62.627, 7.688, 27.1, 4.514, 43.967, and 31.012. Okay, so with Adams's method, what you get is for representatives, you get 63, 8, 28, 5, 44, and 32. Okay, and if you add those things up, 63 plus 8 plus 28 plus 5 plus 44 plus 32, you do get up to 180 total representatives. Okay, so Adams' method gives you this allotment, or gives each of these districts this allotment of representatives. So lastly, I want you to use Webster's method. Find a divisor. Remember, always start standard divisor is 71.84, and you're gonna have to find the divisor to use with Webster's method. Okay, so try that out and push pause on the video, come back and see what you get. Alright, so what I got was that the divisor that we want to use in Webster's method, or at least one of them that you can use, is 72.05, and that did take me a while to get to. Okay, turns out 72.0 doesn't work, it gives you 181. If you do 72.2, that gives you 179. So you ended up having to do 72.05, or at least I had to do 72.05. 72.05. Modified quotas, I got 63.539 for District A, 7.800 for District B, 27.495, 44.580, 44.608, and 31.464. So with Webster's method, standard rounding applies. So this District A gets 64, District B gets 8, District C gets 27, District D gets 5, E gets 45, and F gets 31. All right? And if you add those up, you should get, again, to 180. All right, so that's Webster's method. Again, get a divisor, standard rounding applies. Now we're going to look and compare all of these methods. And I'm trying to point out some of the differences in the methods and the fact that these methods are actually getting different numbers. Okay? So I want you to push pause, fill in all of these numbers, and then come back and see what you have and all of that kind of stuff. Boom. So I've filled all those in, and you can see that, hopefully you filled them in the same way. You can see what's going on here. Notice that each district, none of them are even across the board. Okay, in this example, there's always a method that favors a district. So you can imagine what people are going to do. Okay, obviously District A would fight to have any of these three methods, but they do not want Adams' method. And District B does not want Jefferson's method. Okay? However, while District A doesn't want Adams, District C does want Adams' method or Jefferson's method. Okay? So whichever method somebody picks, one person is going to be out of luck. Okay, that's the idea. So I want you to think about this a little bit, and just assume that you're somebody from, let's say, District C. You obviously want one of these two methods, and here's where sort of the political gamesmanship comes in. You look at those two methods, and you say, okay, I'm better in either Jefferson's or Adams' method. So which one do you lobby for? Do you lobby for a Jefferson's method, or do you lobby for an Adams' method? Okay? If you lobby for a Jefferson's method, then you're going to have A and E on your team. And B and C are going to be against you. If you lobby for Adams' method, A and E are going to be against you. B and D are going to be for you. Now, there's advantages and disadvantages to each one, but think about this. If you argue for Jefferson's method, then the big districts are with you. That may be an advantage to you in the long run. In fact, also F is with you in that case too. F is with you in both of these cases. But the point is, if you have that, you might want to go for Jefferson's method because it puts the big districts on your side. However, you might be somebody who doesn't want to give these big districts an advantage. So if you're somebody who doesn't want to give the big districts an advantage, you might argue for Adams' method. Okay, obviously you want to give your own district an advantage above everybody else. And that's kind of the political gamesmanship that goes around. Obviously none of these methods are equal for every single A, B, C, and D, and F, A, B, C, D, and E, and F. So, there is some jockeying for position and coalition building if you're in one of these districts. And, and it's on all of these. So don't assume that, one district is going to be the only one lobbying. If you're in District C, obviously you want these two methods. So you may, again, if you want the big influential people, maybe you try to convince A and E and F to go with Jeffersons, because that's a lot of votes for you. And you only make these little guys angry. Maybe you take an alternate route and you try to coalesce all the little guys, all the 4 little guys against the big 2 districts. All right? But again, I'm trying to get at the idea of the gamesmanship and why there's all these, why there's a lot of backroom deals in politics in general. But, everybody wants the most representatives for their district. And so how are you going to argue it? How would you argue that if you were District B or District D? And this is just what I said. Notice each district in the example gave different representatives. And if you're an influential person, who would you pick? Which method would you pick and why? All right. So since I've already went over that, I'm not going to take a whole lot of time on that. Now, I want to recap again the problems that came out with every method. If you remember Hamilton's method, we had this Alabama paradox where we increase the number of representatives, but all of a sudden one state loses a rep. We had a population paradox. We had a new state paradox. Population grows in one state and stagnates in the other, but the stagnant state wins more representatives while the growing state loses. That's the population paradox. New state paradox is, if you add one more with 3, based on the divisor, 2 other districts might swap. Okay? But Hamilton's method does have the nice feature that it will always satisfy the quota rule. Now, all the other methods, the Websters Method, Adams's Method, and Jefferson's Method, all of those have potentials of violating the quota rule. And we saw that in one of the methods that we looked at. But again, that could exist in any of those 3 methods that we chose. So sometimes you're arguing for, in this case, what I would say is the lesser of 2 evils. Each one of these apportionment things has kind of weird things that we don't like that could happen. However, you have to pick one and you have to, go abide by that. All right? So that ends the idea of apportionment, and you're going to have to be able to do these kinds of things on a test or a quiz or things like that.